Swayam Prabha. Digital India. Educated India.
Now we are going to discuss some important properties of the probability. Some important properties. The first property. So before that, let me start with let omega capital E of P be a probability space. The first property is P of empty set is 0. In the probability space definition, we have P of omega is equal to 1. So one can prove P of empty set is 0 because empty set is the negation of the whole set. The whole set probability is 1. Therefore, this probability is going to be 0. Second property, if two events A and B belonging to F and both are mutually disjoint events, intersection of events is empty, then if you want to find out the P of A union B, that is same as P of A plus P of B. If two events are mutually exclusive, mutually disjoint events, then the P of A union B, that is same as P of A plus P of B. Otherwise, in general, for any two events, that is P of A union B is P of A plus P of B minus P of A intersection B. Since P A intersection B is empty set and the P of empty set is 0, therefore P of A union B is the same as P of A plus P of B. Third result, for any event A belonging to F, P of A complement, that is same as 1 minus P of A. If you know the probability of A, if you want to find out the probability of A complement, that is same as 1 minus P of A. The same concept is used to find out the probability of empty set is 0 also. The fourth result, for any two events A comma B belonging to F, you can always have a P of A union B, that is same as a P of A plus P of B minus P of A intersection B. As in the result 2, when A intersection B is empty set, then it is going to be just P of A plus P of B. There is no minus P of A intersection B. The next result, result number 5, if A comma B belonging to the F and A contained in B, then one can conclude P of A always less than or equal to P of B. Not only that, P of B slash A, that is same as P of B minus P of A. In particular, P of A is always less than or equal to 1 for all A belonging to F. The next result, let A suffix n be a increasing sequence of events or elements in F. The element in the F is nothing but the events. So let AN be a increasing sequence of elements in F. That is, if you take AN belonging to F and AN is contained in AN plus 1 for all n 1, 2, 3 and so on. That is the meaning of AN be an increasing sequence of elements in F. Then what the result says, the P of limit n tends to infinity AN, that is same as the limit n tends to infinity P of AN, where the limit n tends to infinity AN is nothing but, since ANs are the increasing sequence of elements, limit n tends to infinity AN is nothing but union of n is equal to 1 to infinity AN. Similarly, one can go for sequence of elements which are decreasing. So the next result or next property, that is let AN be a decreasing sequence of elements in F, that is AN belonging to F, and it satisfies for all n is equal to 1, 2 and so on. In this case, P of limit n tends to infinity AN, that is same as again limit n tends to infinity of P of AN, where the limit n tends to infinity AN is nothing but intersection of n is equal to 1 to infinity of ANs, because ANs are the decreasing sequence of elements in F. I am not giving the proof of these results, but it can be proved easily. Now we are moving into the next concept or next definition, that is called a classical definition of probability. A probability space that is omega capital F capital P with finite omega, comma, the F is equal to power set of omega. The P of omega means a power set of omega, and the probability measure of a singleton element W, that is equal to 1 divided by the number of elements in the omega for all W belonging to omega. That is called a classical probability. A classical probability space, because we are defining a probability space. A probability space omega F P with the conditions on omega F as well as P. It's basically a special case of a probability space by satisfying omega is finite and F is the largest sigma field, which is the power set of omega, and the probability measure P is defined on each possible outcome as a 1 divided by total number of elements in the omega, which is finite. for all w belonging to omega. If these three conditions are satisfied by a probability space, then that probability space is called a classical probability space. There is another name for this, that is called a Laplace probability space. In this situation, the probability P is called a classical probability. The probability measure P, which is defined in this probability space with omega is finite and F is the power set of omega, and P on each possible outcome is equilikely, that is 1 divided by number of elements in the omega, then this probability measure is called a classical probability measure, and the probability space is called a classical probability space. So the classical probability space is the special case of the probability space which we have defined it earlier, that is called axiomatic definition of probability. The special case is the classical probability space. Since P on each possible outcome is going to be 1 divided by total number of elements in the omega, so the probability of any event is nothing but number of favorable cases on event A divided by the total possible outcomes, that is whatever the finite number. Suppose A is contained in omega, where A is a event, then P of A is nothing but P of union of singleton elements samples, where all the samples belonging to capital A, the event, that is nothing but summation of W belonging to A 1 divided by that is same as cardinality of A divided by cardinality of omega. In other words, P of A is nothing but a number of favorable cases to the event A divided by number of possible cases. So this is what we have done it in the school days when we are computing the probability of event, that is nothing but the number of favorable cases to the event A divided by the total number of all possible outcomes. So this is going to be the classical probability with the assumption that omega is finite and the sigma field is the largest sigma field, which is nothing but the power set, and equiprobable outcomes. That means P of each possible outcome, that is same as 1 divided by cardinality of omega. So this is called the classical probability space.